Welcome back to another deep dive with us.
Always exciting.
This time, we're going way back.
Oh, yeah.
Back to the early 1900s.
Okay.
To explore the world of atomic physics.
I like it.
Specifically, we're going to delve into the life and work of Niels Bohr.
One of the greats.
Yeah, a man who completely changed the way we think about the atom.
A giant.
We're using excerpts from a biography of Bohr,
Interesting.
focusing on his scientific journey.
Okay.
And wow, it's a story full of twists and turns.
It's remarkable how Bohr's story isn't just about formulas and lab experiments.
Right.
It's about how he questioned the very foundations of science.
Wow.
And the nature of reality itself.
Okay, so our goal today is to understand how Bohr's work
It's a big one.
revolutionized our understanding of the atom,
Okay.
what kind of challenges he faced,
Right.
both personally and scientifically,
Yeah.
and what lasting impact he had on the world of physics.
His impact was huge.
And believe me, his legacy goes far beyond the classroom.
Oh, it does. It's a legacy built on deep thinking
Right.
and a constant desire to question everything.
He was never satisfied,
Bohr wasn't satisfied with just knowing what.
right?
He always wanted to understand why.
That's fascinating. So our story begins in Copenhagen,
Okay.
where Niels Bohr was born in 1885.
All right.
He grew up in a family that valued intellectual pursuits.
Sounds like a good environment.
Yeah, and his father was a respected physiology professor at
Right,
the
no.
University of Copenhagen,
Oh, wait.
would frequently host gatherings with prominent scientists
I see.
right in their home.
Wow.
Can you imagine the dinner conversations?
That environment was like a breeding ground
Right.
for scientific curiosity.
Yeah.
It's no coincidence that Bohr's brother, Harold,
Oh, yeah.
became a renowned mathematician.
Wow.
They were constantly surrounded by stimulating discussions.
You're right. It wasn't just passively listening in for them.
No.
Imagine.
No.
Bohr and his brother formed a discussion group called Ecliptica
That's a cool name.
with a bunch of their friends from different fields.
Wow. So
Yeah.
interdisciplinary.
They tackled some pretty weighty topics.
Like what?
They debated everything from the philosophy of science
I see.
to the limits of human knowledge.
Those are big questions.
I know.
This early experience of collaboration
Yeah.
and the challenge of defending his ideas
Right.
clearly shaped Bohr's approach to scientific inquiry.
It's like they were a mini think tank.
Yeah.
But to truly grasp the magnitude of Bohr's work,
Okay.
you need to understand the state of physics
Yeah.
at the beginning of the 20th century.
A very different time.
It was a time of immense change and a bit of chaos.
Yeah.
With scientists wrestling with really fundamental questions
Right.
about matter and energy.
The big stuff.
It was like the Wild West of physics.
I can see that.
Imagine scientists back then were like explorers venturing into uncharted territory.
Yeah.
Bohr's insights became the map
The map.
they desperately needed.
Before Bohr came along,
Right.
you had pioneers like John Dalton,
Okay.
who developed the first modern atomic theory,
Right.
proposing that everything is made up of
Yeah.
these tiny indivisible particles called atoms.
Adams.
Dalton's work was groundbreaking.
That was.
But the story doesn't end there.
Of course not.
Then you have Dmitri Mendeleev
Right.
and his amazing periodic table.
Yeah.
The way he organized the elements
I know, it's amazing.
really hinted at a deeper structure within the atom itself.
It's like he cracked a secret code of the universe.
Yeah.
But there was still this debate raging on about whether atoms were actually real physical things
What?
or just convenient theoretical ideas.
No way.
It's hard to believe that something we take for granted today
I know.
was still up for debate back then.
Here's where the development of statistical physics becomes crucial.
Okay.
Scientists like James Clerk Maxwell and Ludwig Boltzmann
Okay.
applied statistical methods,
Okay.
the kind used to understand things like
Yeah.
the spread of diseases or population trends,
Right.
to figure out how gases behave
Interesting.
and their findings.
What did they find?
Well, they provided strong evidence
Okay.
that atoms were indeed real
What?
physical entities.
So they used math
Yeah,
to uncover the secrets of the invisible world.
it's pretty amazing.
That's pretty awesome.
But then the discovery of the electron threw another curveball into the mix.
Oh, no.
J.J. Thomson's discovery of the electron
Okay.
completely shattered the idea of the
Yeah.
atom as a solid, indivisible unit.
Wow.
It was clear that the atom had internal parts,
Okay.
leading Thomson to propose his famous plum pudding model.
Plum pudding.
Think of it like this. Negatively charged electrons,
Okay.
the plums,
Okay.
embedded in a positively charged pudding.
That's a delicious analogy.
But was it accurate?
Was it?
Not quite.
Okay.
Thomson's model, though, a step in the right direction.
Right.
Couldn't explain some experimental results.
Okay.
Particularly those from Ernest Rutherford's famous gold foil experiment.
Ah, Rutherford, another legend in physics.
Absolutely.
He basically shot alpha particles,
Okay.
which are like tiny bullets made of helium nuclei,
Right.
at a super thin sheet of gold foil.
Okay.
The results were shocking.
Oh.
Most of the particles went straight through,
Mm.
but a small percentage were deflected at sharp angles.
Okay.
Some even bouncing straight back. Hey, can you believe that?
That unexpected result
I know.
led Rutherford to propose his nuclear model of the atom.
Okay.
Picture this. A tiny,
Okay.
incredibly dense,
Okay.
positively charged nucleus in the center,
Right.
with electrons orbiting around it,
Okay.
like planets around the sun.
It's amazing how they were able to piece together the atom structure from these experiments.
It is.
But Rutherford's model had a major problem.
Ow.
Think about it.
Okay.
According to the laws of physics at the time,
Right.
electrons zipping around the nucleus should constantly be losing energy and spiraling inward,
Oh, no.
causing the atom to collapse.
Right.
But obviously, atoms don't just collapse.
It does.
So something was missing in this picture.
So what happened?
And that's where Niels Bohr steps onto the scene.
Here he comes.
He took on this challenge head-on
Okay.
by introducing a revolutionary concept, the idea of quantized energy levels.
Well,
it's like he rewrote the rules of the game.
Bohr took inspiration from Max Planck's quantum hypothesis,
Okay.
which proposed that energy
Right.
isn't a smooth, continuous flow,
Okay.
but comes in discrete packets or quanta.
Quanta?
Bohr applied this idea to the atom,
I see.
suggesting that electrons can only exist in specific orbits
Okay.
with fixed energy levels.
So instead of those spiraling electrons crashing into the nucleus, Bohr envisioned them making these sudden quantum leaks
Quantum leaps.
between orbits, absorbing or emitting energy in the form of light,
Okay.
only when they change energy levels. It's like they're on a staircase,
Okay.
and they can only be on specific steps,
I see.
not in between.
And what's even more remarkable
Go on.
is that Bohr's model perfectly explained the observed spectrum of hydrogen,
Wow.
the simplest atom,
Okay.
the specific wavelengths of light emitted by hydrogen,
Right.
which had puzzled scientists for ages,
Yeah.
could now be predicted accurately using Bohr's model.
That's incredible.
It was a huge victory
I know.
for the emerging world of quantum physics.
A big win for the quantum team.
Yes.
But it didn't stop there.
Of course not.
Another brilliant physicist,
Who?
Arnold Sommerfeld,
Okay.
refined Bohr's model by introducing the concept of elliptical orbits for electrons,
Elliptical orbits.
adding even more detail to the picture.
Sommerfeld's contribution suggested that electron orbits
Right.
weren't just simple circles,
Okay.
but could also be oval-shaped,
Interesting.
with varying degrees of stretch.
Stretch.
This helped explain the fine structure of the hydrogen spectrum.
Oh, wow.
Those tiny variations in spectral lines
Okay.
that Bohr's original model couldn't fully account for.
It's like zooming in on a picture
Right.
and discovering a whole new level of detail that you hadn't noticed before.
Exactly.
But even with these advancements,
Right.
Bohr knew there was more to uncover.
Always more to learn.
He was on a quest to find a deeper connection
A deeper connection.
between the seemingly contradictory worlds of classical physics and the new quantum realm.
What did that lead to?
Well, it led him to formulate the principle of correspondence.
Okay.
This guiding principle aimed to bridge the gap between the two realms.
So a bridge between the old and the new?
Bohr argued that quantum behavior should seamlessly blend into classical behavior
Okay.
as you scale up to larger systems
Right.
and higher energies.
In simpler terms.
Right.
As you move from the microscopic world of atoms
Okay.
to the macroscopic world of everyday objects,
Okay.
the strangeness of quantum mechanics should fade away.
Yeah.
And the familiar rules of classical physics should take over.
Exactly.
But despite these insights,
All right.
the limitations of the Bohr-Sommerfeld model
No.
in explaining more complex atoms
Yeah.
became increasingly apparent.
Mm.
A new revolution in physics was on the horizon.
And with that, we come to the emergence of a more complete theory
The more complete theory.
of quantum mechanics,
Okay.
with giants like Werner Heisenberg and Erwin Schrödinger entering the scene.
By heavy hitters.
But that's a story for our next segment.
Okay, wait.
So stay tuned.
I will. welcome back.
All right, so...
When we left off, the world of atomic physics was on the verge of another major upheaval.
Uh-oh.
This time, it was the discovery of the neutron.
Neutron.
That would shake things up.
Okay.
It turns out the atom, far from being a simple entity, was a universe in itself.
Wow.
Full of unexpected twists and turns.
I love how each new discovery seems to unlock even more questions and mysteries.
Always more to learn.
Speaking of mysteries,
okay,
let's talk about the neutron.
Right.
Who discovered it, and what made it such a game changer?
The credit for discovering the neutron goes to James Chadwick.
James Chadwick?
Who was working at the Cavendish Laboratory in England.
Okay.
Back in 1932.
Right.
He was studying a very strange type of radiation.
Okay.
That was released when beryllium was bombarded with alpha particles.
So once again, we have scientists smashing particles together.
Pretty much.
And eagerly observing the results.
Observing very carefully.
Kind of like a subatomic demolition derby, right?
You could say that.
But the results were far from predictable.
No, they weren't.
Chadwick's experiments showed that this mysterious radiation wasn't like gamma rays, which are electromagnetic.
Yeah.
Instead, it behaved like a stream of neutral particles.
Okay.
Each with a mass similar to a proton.
Interesting.
So not just a new particle, but a whole new kind of particle.
Right.
One with no electric charge.
That's right.
That's a huge deal.
It is.
It's like finding a new element.
Yeah.
But on a subatomic level.
Exactly.
The neutron's discovery was a monumental event.
It really was.
It finally gave scientists the missing piece.
Yeah, okay.
They needed to fully understand what the atomic nucleus was made of.
They had struggled for so long.
Now that you mention it, I vaguely remember learning that.
Okay.
That before the neutron, the nucleus was thought to contain protons and electrons?
That was the idea.
But that always seemed a bit odd to me.
You're right to be skeptical.
Oh, yeah.
That model had all sorts of problems.
Okay.
The neutron's discovery provided the solution.
A much-needed solution.
And it did so much more.
What else?
It opened up completely new fields of research.
Like what?
Like the possibility of manipulating the nucleus itself.
And that leads us to the birth of nuclear physics.
Nuclear physics.
A field that would have a monumental impact.
Absolutely. Not just on science, but on the world as a whole.
You can't overstate the significance.
Right.
But the discovery of the neutron wasn't the only surprise in store.
There's more.
Oh, yeah.
Okay.
Around the same time, Carl David Anderson, working with cosmic rays, stumbled upon another mind-blowing discovery. What's that?
The positron.
A positron.
Yeah.
The name sounds a bit like something out of a science fiction movie.
It does a bit.
What is it exactly?
Think of it as the electron's mirror image.
Okay.
Or its evil twin, if you like.
Okay.
The positron is essentially an electron.
Right.
But with a positive charge.
Okay.
Instead of a negative one.
Okay.
Anderson was studying the tracks.
Okay.
Left by cosmic ray particles. In a cloud chamber.
Yeah.
When he observed these strange particles curving in the opposite direction to what you'd expect from an electron.
So you're telling me that for every particle, there's an antiparticle out there.
That's the idea.
Lurking in the universe with the opposite charge.
Right.
It's like the universe has its own hidden mirror image world.
That's exactly right.
Wow.
And it's a concept that has its roots in theoretical physics.
Okay.
Paul Dirac, a brilliant theoretical physicist, actually predicted the existence of the positron.
Really?
Years before Anderson's experimental discovery.
Wow.
He did this while working on a relativistic equation to describe the electron.
Another amazing example of how theoretical predictions can lead to groundbreaking discoveries.
Sometimes that's how it happens.
It's like science has its own built-in compass guiding us towards the truth.
It's a beautiful dance between theory and experiment, each pushing the other forward.
I like that.
The discovery of the positron had immense implications.
Okay, like what?
It confirmed that antimatter wasn't just a theoretical concept.
Right.
It was real.
Wow.
It also raised the question of why we see so much more matter than antimatter in the universe.
Right.
Where did all the antimatter go?
That's a good question.
It's a question that continues to baffle scientists today.
Talk about a cosmic mystery.
I know.
But let's get back to the nucleus for a moment.
Oh.
With the discovery of the neutron and positron,
Right.
scientists were finally able to dig deeper into the processes happening inside the nucleus, like radioactive decay.
The radioactive decay?
Essentially, when an unstable atomic nucleus decides to become more stable by emitting particles or energy, it's like the nucleus is trying to find a more comfortable configuration.
So it's like the atom is rearranging its furniture to create a more harmonious space.
But there were still a lot of unanswered questions about how this process actually worked.
Like what?
Didn't you mention something earlier?
I did.
About a debate regarding the energy of beta particles.
Yes, you have a good memory. Beta particles are high-energy electrons that are emitted during certain types of radioactive decay.
Right.
The question was whether their energy spectrum was continuous, meaning they could have a range of energies, or discrete, meaning they could only have specific energy values.
If I recall correctly, that debate was linked to a very fundamental question in physics.
Go on.
The conservation of energy.
The conservation of energy.
Didn't some scientists, even Bohr for a brief time, think that maybe energy wasn't always conserved in radioactive decay?
You're absolutely right.
Wow.
The idea of energy not being conserved was a radical one. A desperate attempt to explain the seemingly continuous energy spectrum of beta particles.
Yeah.
But it ultimately didn't hold up.
So what did?
It was Wolfgang Pauli.
Wolfgang Pauli.
A brilliant and independent young physicist who offered a bold and ultimately correct solution.
What was it?
He proposed the existence of a new, as yet undetected particle.
A new particle.
That was carrying away the missing energy.
And that particle was later named the neutrino, right?
That's right.
The elusive little ghost particle that interacts so weakly with matter.
It does.
That it was incredibly difficult to detect. The neutrino, a neutral particle with very little mass, was a theoretical concept for many years.
It was.
It took decades of ingenious experiments.
It really did.
Before it was finally detected in 1956.
Wow.
Confirming Pauli's bold prediction.
It's another testament to the power of theoretical physics.
Right.
To guide us toward new discoveries.
But the neutrino was just one piece of the puzzle.
Right.
Scientists were also eager to understand what was holding the nucleus together in the first place.
That's a big question.
After all, if the nucleus is made of positively charged protons and neutral neutrons, why doesn't it just fly apart due to electrostatic repulsion? It's like trying to squeeze together the same poles of a magnet.
I see what you mean.
They just want to push each other away.
It's a brilliant question.
It is.
And it led to the development of the concept of the strong nuclear force.
The strong nuclear force.
One of the 4 fundamental forces of nature.
Oh, wow.
This force is incredibly strong at short distances.
Okay.
Much stronger than the electrostatic repulsion between protons.
Okay.
It's what binds the nucleus together.
So it's like a tiny but mighty force that keeps the atom's core from bursting apart?
But as scientists delved deeper into the nucleus, they realized they needed more powerful tools to unlock its secrets.
Like what?
That's where particle accelerators came into the picture, right?
Particle accelerators?
Those giant machines that smash particles together.
Wow.
At mind-bogglingly high speeds.
They sound like something straight out of science fiction.
They kind of are.
But they've become indispensable tools for understanding the fundamental building blocks of the universe.
Absolutely.
And Bohr, always a champion of scientific progress, recognized the importance of these new tools.
He did.
He pushed for the construction of a cyclotron, a type of particle accelerator, at his institute in Copenhagen.
Wow.
Paving the way for future discoveries.
Amazing.
So Bohr wasn't just the theoretical genius.
No.
He was also a visionary leader.
He was.
Understanding that both theoretical and experimental advancements are crucial for pushing the boundaries of knowledge.
It takes both.
But as the world plunged into a period of conflict, with the rise of Nazi Germany, Bohr's leadership would extend far beyond the lab.
I see.
As he became a vocal advocate for scientists facing persecution.
Wow.
And a key figure in the development of atomic energy.
And that's where we'll pick up in our next segment.
Okay.
Exploring the later years of Bohr's life and his lasting legacy.
Stay tuned. Welcome back to the Deep Dive.
Glad to be back.
Last time we left off with the world on the brink of war.
Right.
And Niels Bohr facing a new set of challenges.
New challenges.
Not within the equations of physics.
Okay.
But in the realm of human conflict.
A different kind of challenge.
It's a story that takes a turn.
A turn.
From the theoretical to the deeply personal.
This is where Bohr's story becomes incredibly moving.
Yeah.
As Nazi Germany's shadow spread across Europe.
Right.
Bohr became more and more involved in helping scientists who were being persecuted. Imagine his institute in Copenhagen becoming a safe haven, offering refuge to those fleeing the horrors of the Nazi regime.
It's inspiring to think of him using his position and influence, not just for science, but to make a real difference in the lives of people facing such unimaginable hardship.
It really shows the kind of person he was.
It truly speaks to his character.
It does.
And his unwavering belief in human values.
But Bohr's efforts didn't stop at providing shelter in Copenhagen.
No.
He used his network of connections.
Okay.
Especially with the Rockefeller Foundation.
Right.
To help these displaced scientists find new positions in other countries.
That's amazing.
Picture him working tirelessly.
Okay.
Writing letters.
Wow.
Making phone calls, doing everything he could to ensure that scientific knowledge and talent wouldn't be extinguished by the darkness of war.
It's a testament to the idea that science thrives on collaboration.
It does.
On the open exchange of ideas across borders.
Which is so important.
Bohr clearly understood that silencing scientists, whether through persecution or isolation, ultimately harms the progress of knowledge itself.
It's a stark reminder that even in the darkest of times, the actions of one person can make a difference.
They really can.
Bohr's actions during this period were heroic. A beacon of light in a world consumed by shadows.
But then the war brought another step.
Far more complex challenge. The development of atomic weapons.
This is where this story takes on a whole new level of weight.
It does.
Bohr became deeply involved in the Manhattan Project.
The Manhattan Project.
Top secret race to build the atomic bomb.
It's a controversial chapter in his life.
It is.
Raising profound ethical questions. About the role of scientists in war.
You have to consider the context.
Right.
The world was at war.
Yeah.
And the threat posed by Nazi Germany was very real.
It was.
Many scientists at the time, including Bohr, believed that developing atomic weapons was a necessary evil.
A necessary
way to prevent the Nazis from acquiring this terrifying power first.
It was a race against time.
It was.
With the fate of the world hanging in the balance.
But even as he worked on the Manhattan Project, Bohr was already wrestling with the implications of this new weapon.
He became increasingly concerned.
He did.
About the need for international control of atomic energy.
Seeing the potential for global catastrophe.
Right.
If this power fell into the wrong hands.
Bohr envisioned a world open to scientific exchange. A world where nuclear energy would be used for peaceful purposes.
Wow.
For the benefit of humanity.
What a powerful vision.
It was.
But tragically, it clashed with the realities of the emerging Cold War.
Right.
Bohr's pleas for openness and international cooperation were met with resistance. Particularly from political leaders in the United States and Great Britain.
I see.
They were more focused on maintaining their own nuclear advantage than on sharing this knowledge with potential rivals.
That's a tragic irony.
Yeah.
The very technology that was developed to prevent tyranny became a source of division and fear, fueling a global arms race that threatened the very survival of humanity.
Bohr was caught in a moral dilemma.
He was.
How to reconcile the scientific drive to understand and control nuclear energy with the urgent need to prevent its misuse.
It's a dilemma that still resonates today.
I think you're right.
As we grapple with new technologies that have the potential for both good and harm.
Absolutely.
Bohr's story reminds us
that
scientific knowledge comes with great responsibility.
So what happened to Bohr's dream of a world open to scientific exchange?
Wow.
Did his vision ever come to fruition?
While his dream of a world free from nuclear weapons hasn't yet been fully realized, Bohr's efforts laid the groundwork for important international organizations like the International Atomic Energy Agency. They work to promote the peaceful use of nuclear energy,
Right?
and prevent its proliferation for military purposes.
It's a testament to his lasting legacy.
It is.
He wasn't just a brilliant physicist who revolutionized our understanding of the atom.
Absolutely.
He's also a humanist.
A humanist.
A visionary leader who understood the profound impact of science on society and who strived to guide its development towards a better future.
Bohr's journey shows us
Yeah.
that scientific progress
Right.
is not just about formulas and experiments.
It's not.
It's about asking the right questions,
Okay.
challenging what we think we know,
Right.
and being willing to engage in open and honest conversations,
Yeah.
even when those conversations are difficult.
They can be tough.
It's about recognizing how science and society are intertwined
They are.
and using our knowledge to create a more just,
Right.
peaceful, and sustainable world.
What a powerful legacy.
It is.
Bohr's life and work show that seeking knowledge isn't just about unlocking the secrets of the universe,
Right.
but also about unlocking our own potential as human beings,
I like that.
using our understanding to create a better path forward.
And with that thought,
Yeah.
we wrap up our deep dive into the world of Niels Bohr.
What a journey.
It's a story that reminds us all
Okay.
of the importance of curiosity,
Curiosity.
courage, and responsibility
Responsibility.
in the face of new discoveries.
Thank you for joining us on this journey.
It's been a pleasure.
And we hope you'll join us next time
I hope so.
for another deep dive into the world of knowledge and ideas.
Sounds good.
Until then, keep asking those big questions
Keep asking.
and never stop exploring.
Never stop exploring.